This is the picture, at least in North America, over the last 2 decades, where what we've seen is, if you look at hospitals around America and Canada, the adoption of electronic medical records has dramatically increased in the last 2 decades. And I imagine countries around the world have a similar or better picture, actually, in terms of how well and how long they've been using electronic medical records. But if we look at what is in those electronic medical records, it comprises medical images, inpatient health monitoring data, medical examinations, patient-generated health data, as well as laboratory test results. And if we think as all of this data as representing proxies for some underlying latent physiological process that is going poorly in the context of a diseased patient, then what this data give us are views into a patient's underlying physiological state. And this brings about new opportunities. And so one of the core thrusts of the group that I run is thinking about how we can realize this vision of a learning healthcare system, where we might start with some of this electronic medical record data, and we might use the data to build clinical decision support tools. And so those clinical decision support tools might be things like predicting outcomes in hospitals, improving resource utilizations, as well as finding digital twins. And now, once we have these tools routinely running in hospital systems, we might be able to also help accelerate the discovery of scientific processes that occur in a variety of scales in the human body. And eventually, those discoveries sort of find their way back into the electronic medical records as new biomarkers, and the cycle kind of repeats. And in the context of this cycle, what I really want to focus on today is the idea of predicting outcomes in healthcare. And specifically, how can we do so safely? And how can we build statistical guardrails for the safe deployment of predictive models in healthcare? So I'm not going to emphasize a lot about the development of predictive models in healthcare. Rather, I'm going to think about how we can do so to build mechanisms to ensure that these models are deployed safely. So I'm going to focus here on this idea of risk scores as predictive models in medicine. And so, risk scores have been used traditionally in medicine over the decades. And so if you look at something like the Framingham Heart Study, it's essentially it's a tree-based model, or a decision tree that continues, and you enter a set of features about the patient, and it prints out an assessment of the patient's heart risk. And now that we have things like neural networks that can be trained on large data sets, we're able to solve predictive tasks such as identifying skin lesions, as well as making predictions from incredibly large histopathological images. And so the paper on the right is an example of some work that we did at CVPR last year. But these algorithms are not perfect. And so even if we have very good predictive models, they can still fail. And so I've highlighted 2 articles here that made waves in the press, at least in North America, that talk about how some of these predictive models might fail. So for context, the first article talked about a model to predict the risk of sepsis. And so this model was developed by Epic, which is a company that makes electronic medical record software in North America. And that company decided to deploy this predictive risk score for sepsis. But when a researcher out of the Michigan medical system decided to study how well it performed, he identified that it essentially had an incredibly high false alarm rate. And so this model was very miscalibrated and was predicting quite poorly in the population in Michigan. And in addition to these kinds of failures, there's also failures due to the fairness of this model. So why do these failures come about? And so just to motivate the problem and really the need for these statistical guardrails, I want to highlight the fact that healthcare is one of those scenarios where data set shift is very, very prevalent. It's a scenario where the data distribution at training time is very different from the data distribution at deployment or test time. And these changes in the distribution of covariates can alter the predictive performance of the model. And so we're familiar with the idea that where models are developed with this notion that they're going to be deployed in settings that are IID from the training set, but that's never true in practice when they're actually used. And so if you take a model and deploy it in a new hospital, or if you take the same model and look at how it performs over time, you will consistently see degradations in performance. So really the goal when my student Tom and I started thinking about this problem was, how do we build wrappers to ensure that machine learning models are deployed safely in healthcare? And I should say here that this is not a new idea. There's been a ton of work in this space, including this book that I'm going to highlight that was edited by Musashi, highlighting some of the work in machine learning that's been invested in trying to understand and build methods to detect covariate shift. And so the references on the left-hand side are some of the highlights from the more recent years, but as I said, people have been studying this problem for over 2 decades. So if we were to cluster some of the limitations of the existing methods that we actually ended up trying in the context of the healthcare problems that we'll get to at the end of the talk, what we found were 2 limitations. We found that methods often needed a larger number of samples to detect covariate shift in a sensitive manner. And the second was that there was a lot of emphasis, at least in the recent literature, on detecting covariate shift in neural networks. And while neural networks are predominantly used in medical imaging, they are not the only class of statistical model that finds use in healthcare. In healthcare scenarios, as I mentioned earlier, you might have decision trees and XGBoost style models, which are actually very popular for modeling predictive outcomes with tabular data. So what do we need? We need, and I should say that these limitations have very practical impacts on how models perform in healthcare. So, if it takes more samples to detect shift, that effectively means that there's a larger number of patients who are being considered in the healthcare system with a model that is subpar. And so what we need are mechanisms to detect shift quickly, and we need mechanisms to detect shift in a manner that is agnostic to the class of underlying model that's used. And so that brings us to the idea that I'm going to highlight today, which is that of the detectron. And so this is work that was led by my master's student, Tom, who is somewhere, who I hope is attending today. I see his name. And the idea behind this is to use the classifier that we already have to devise a learning-based hypothesis test to identify harmful covariate shift. And so this is a paper that we'll be presenting this year at ICLR in the coming few months. So just to set up some notation and some goals, I'll go through this paper at a very high level, and I won't jump into a lot of the details, but my goal is really to give you some intuition for how the algorithm works. So we have a classifier F that is trained on some data set P that is sampled IID, and then F is taken and deployed. And what we would like is, and as F is deployed, it comes into contact with unlabeled samples Q. And so Q are drawn IID from some unknown distribution. And what we would like is a mechanism to leverage the classifier that we have to design a 2-sample test for covariate shift between P and Q. And we'd like it to have the property that it should work when the number of observed test samples is quite small. That is, the set size of Q should be much less than the set size of P. And so the advantage of the reason we do it this way is that we want to find a very sensitive test for detecting shift, so that the moment the data science team at the hospital recognizes that the model is not performant anymore, they can choose to replace it. I should say that one very naive mechanism to solve the problem of stale models in healthcare might simply be to wait until the labels are actually recovered and look at the generalization error of the classifier. And when it drops below a threshold, replace the model then. So I should say that that works, except when the labels that you're predicting happen well into the future. If you're predicting the outcome of a patient that happens in 6 months, and the model is not working anymore, you're going to have to use 6 months of time before you realize that model has actually failed, because 6 months ahead of time is when those labels are available. So really, we want a mechanism that works even in the absence of those labels. And so the pipeline looks something like this. So on the left-hand side is our original model, the pre-trained model F that we're considering for deployment. And we're going to construct this test in 3 steps. So the first step is what we call this fine-tuning step, where we take our classifier F and we fine-tune it to disagree on IID data. So this is data from, say, a validation set. And we'd like to train this classifier to disagree on this data. And we're going to do that under the constraint that it must agree with F on the training set. So what is this notion of agreement and disagreement? So that's what I've listed at the bottom here, which is that training for disagreement intuitively means we want to encourage the classifier to predict a label given data that is different from the label predicted by the pre-trained model. So for the set of samples from P sub X, we're going to first use the model to predict a set of labels, and then we're going to fine-tune a classifier to disagree with them. So in the binary case, it would be flipping the labels, while still predicting accurately on the labels from the original training set. So that's step one. We're going to repeat a very similar step, that's step 2 at the bottom part of this graph, where we fine-tune F or another clone of F to disagree on observed data that is not from unlabeled samples. So this is this candidate set of samples Q that we're observing only at deployment time, and we don't know whether this set Q represents samples that are shifted or not. And once again, we're going to fine-tune F to disagree on Q while constraining it to agree with F on the training set. And step 3 is the computation of the test, where we're just going to compare the disagreement rates and use this comparison as a test statistic for covariate shift. So the first step, just to go through it in a little more detail, is to take our classifier F and ask it to disagree on IID samples from a validation set. And so this graphic that you see at the bottom right represents the degree to which these classifiers, in practice, it's an ensemble of classifiers. And so that's why you get this histogram. And we train these models to predict the opposite labels on in-distribution data. Step B, we train models to predict the opposite set of labels on out-of-distribution data. And step C is simply to compare the statistics of how much models disagree on held out data from P versus their disagreement rates on held out data from Q. And the intuition that we're really leveraging here is that it's easier to learn to flip labels on out of distribution data than in distribution data for very, very flexible model families. And and that's it. So that's really the algorithm that we have. And in the paper, we go into a lot more depth about the theoretical ability to identify covariate shift based on disagreement rates in the finite sample regime. I should say that there's still a lot more room to understand when and why this algorithm works, but I'm going to show you some of the kinds of results that we've gotten on 3 different data sets. And so the first 2 data sets are image-based data sets where we're going to use neural networks as predictive models. And the last data set is a tabular data set of outcomes where we're going to use an XGBoost model as the predictive model that is actually being considered for deployment. So as you can see, this method is something that works in the context of either a neural network-based model or a XGBoost-based model. And we compare to a variety of different methods that have been proposed in the literature. And for some of these methods, we had to figure out how best to adapt them to the XGBoost regime because it wasn't always readily a sensible thing to do in that regime. So the CFAR10 example is one where we trained on the CFAR10 dataset and we evaluated on CFAR 10.1. And so CFAR 10.1 is a new set of images that was, I think, it's a new dataset that was created about a decade after the CFAR 10 dataset. And visually, it looks quite similar to the CFAR 10 data, but there are subtle differences in terms of how the data has shifted. And so it presents a really interesting benchmark. And what we find here, maybe I'll go on to the middle column now, which is the Camelon dataset, which is building predictive models of histopathological image slides. And so here the shifts are around which hospital the slides actually come from. And finally, the UCI heart dataset, which is around which location or subgroup of patients the data actually comes from. And in each of these cases, if we look at the power at a 5% significance level, we find that we're able to detect shift to a fairly good degree of accuracy, even with as few as 20 unlabeled samples. And so that's kind of the empirical study that we did in the context of the RIKEN paper, but we wanted to go back to the original motivation for why we wrote this paper, which is to understand whether this presents a viable mechanism for operating on real healthcare data, and whether this presents a viable way for us to develop a deployable guardrail for predictive models in healthcare. And to study this question, we leveraged this resource called Gemini. So Gemini is a network data set of data from 31 different hospitals and 20 healthcare organizations in Ontario, which is the province that Toronto is located in. And so this has about 1.3 unique hospitalizations that happened between April 2015 and September 2022. For our study, we looked at a subset of the original Gemini data set, which was 7 hospitals at 5 healthcare organizations in the Greater Toronto area. So this was a very large data set, and we had about 206,000 patient encounters with about 125,000 unique patients. And so we plotted, the distribution of where these patients came from. And obviously there's a non-trivial and large cluster coming out of the Ontario area, but these patients actually come from a lot of places in North America, as well as a few places in Western Europe. And so, to assess the degree to which our model the degree to which we can actually build some guardrails in healthcare, we had to come up with a predictive model. And so one predictive model that we studied in this context was a predictive model of mortality, which in and of itself is an interesting learning problem. And so we built a model to predict inpatient mortality using the clinical data that was available in the Gemini data set. And so the feature set for this included diagnoses that are added as yes or no indicators. And we added diagnoses into the model in order of prevalence in the population. And we plotted the degree of performance as a function of the number of diagnosis codes added, and cut it off at a threshold where we felt that enough of the variance in the outcome was explained by the diagnosis codes added. And we use a similar criteria for selecting labs, vitals, interventions, and pharmacy data within the first 48 hours of admission. And our goal was really to predict mortality, which is whether or not the patient would survive in the next certain period of time for this patient. The reason why this was an interesting and clinically useful model is that it's something that the doctors are actually studying in Toronto right now as a mechanism for risk stratification and point of care. So how do you understand how to spend scarce resources within a hospital institution that has a really fast-moving and fast-paced environment? They might use machine learning to try and stratify patients, and this is one approximation to a model that might help them do that. And so the model that we use here was just XGBoost to predict mortality, and we used Gemini to simulate a variety of different deployment scenarios in healthcare. So one of the key advantages of working with a really rich data set like Gemini, because it spans so many hospitals in such a long period of time, is that we can actually study how a model might behave using retrospective data. So we can study how a model might behave if it were deployed, but we actually have labels so we can do things like study the drops in generalization error. And in this particular example, what we did is we trained on 5 of the different hospitals and tested the model on the other hospitals. So what you see here is a plot where along the rows are the training institutions and along the columns are the testing institutions. And the numbers that you see are the held out area and the receiver operating curves for the binary prediction model that we had of 30-day mortality. So does a patient live or die within that window of time? And what's highlighted in red are a certain set of scenarios where the model exhibits poor transfer. So a model that is trained on MSH does not seem to transfer well to any of the other hospital institutions. And this is just us verifying that this data set was actually a meaningful resource for us to build out a framework for studying guardrails in healthcare. And the same is true over time, where we plotted the empirical performance of these models over time and saw that indeed there were scenarios where the area under the receiving operating curve, particularly the ones in brown and red, dropped as we crossed the threshold from 2019 into 2020 and 2021. And so really here in healthcare, distribution shift describes a sort of general phenomena, and real world samples are not exchangeable with training samples. And misspecification can occur when there are multiple models that appear valid for a given task. And so what we're going to try now is to understand how useful the detectron is in the context of Gemini. And so here, this is an example of running the detectron model in the particular scenario where we have a model that's trained on one domain and tested on a variety of different other domains. And so you can see on the y-axis, we're plotting the disagreement rate, where, remember, a larger amount of disagreement between a rate indicates that there's a higher degree of possible shift or model misspecification, and consequently indicates to the practitioner that they should not consider deploying this model in the specific hospital institution. The names are sort of irrelevant in this case, and they're just indicative of different population sets that lie within the hospital systems in Toronto. And so in summary, and I'll wrap up soon, I motivated the need for statistical guardrails for models that are deployed in a variety of high-risk settings. And really, this is just our initial attempt at a framework to try and build something to solve this problem. So we leverage the idea of how to use disagreements between classifiers to come up with a number that characterized the degree to which covariate shift might occur. And I didn't show results on this, but that number also correlates with the drop in generalization error of the classifier in new domains. So that's an interesting independent finding. And the method itself is very easy to implement, and it seems to work across a variety of different modalities of predictive models. So it works on image models as well as on the tabular XGBoost style models that we developed. And so my student Tom has done an incredible job in sort of packaging this into a really nice Python-based API that you can train very, very quickly. And so I wanted to shout out to that as well. And finally, thank you to the variety of groups that fund this kind of research, as well as a lot of credit to Tom, who sort of spearheaded this work in collaboration with Zhang and Fahad and Razak, the clinical collaborators that we work with at Gemini. So with that, I will stop. I think that puts me at about under a minute for time, but thank you so much, and I'm happy to take questions.
This is Jingfeng. I'm a postdoc with Professor Sugiyama at RIKEN AIP. Today, I'm going to talk about the application of adversarial robustness. I will cover two aspects: backgrounds and case studies on how to use the adversarial robustness. Let's look at the point one. We know that adversarial attack can evaluate the vulnerability of machine learning models because machine learning models are sensitive to the input perturbations. For example, with only small noise, the image of pig will be wrongly recognized as an airliner. How to construct the adversarial data? We basically solve a constraint optimization problem. Given a machine learning model and its loss function, we output the adversarial data, maximizing the loss within the no-ball. Adversarial data are the no-ball constraint, the same semantic meaning between the natural data and the adversarial data. The epsilon control the size of the no-ball. Project gradient descent, PGD, approximately solve this constraint optimization problem. Given a starting point, TGD calculate the gradient of the loss function with respect to the input. Gradient is a direction pointing to a place with a slightly larger loss. Now we have a new point whose loss is slightly larger than the natural data. Then we calculate the gradient again. The loss of yellow point is again larger, so on and so forth. Finally, we have a red point with the highest loss, which can make machine learning model inaccurate. Why machine learning models are so vulnerable to the adversarial attack? Because standard training output a model whose decision boundary is near the data. Therefore, when we slightly perturb the near decision boundary data, like these are denoted by red, the model will make mistakes. Even worse, due to the curse of high dimensionality, almost all data are near the decision boundary. To meet the above challenge, we have a new learning style that is adversarial training. Adversarial training has two purposes. First is to correctly classify the data, that is, increase the natural accuracy on the natural test data. Second, unlike those standard training, adversarial training outputs a thick decision model. Therefore, data are encouraged to be further away from the decision boundary. The learning objective of the vanilla adversarial training is the minimax formulation. Inside, there is a maximization where we commonly use the PGD method to generate the adversarial data within the non-Borel constraint. Outside, there is a minimization where we can find a classifier to fit those generated adversarial data. To realize this learning objective, we use alternating optimization technique. At each epoch, adversarial training conducts step 1 and step 2 alternatively, generating the adversarial data and then minimizing the loss of those generated adversarial data. In comparison, at each epoch, standard training only minimizes the loss on those natural data. Now I'm going to consider how to leverage the adversarial attack and how to use the adversarial training in the following two case studies. We know that adversarial attack is a way of uncovering the vulnerability of machine learning model, and adversarial training is a way of making those machine learning models robust against those vulnerabilities. Then, in the following slides, I will use attacks and adversarial training in deep image denoisers and non-parametric two-sample test. Image denoising is to reconstruct clean images from their noisy observations. Therefore, it is commonly used in medical images, satellites, and cameras. In image denoising, the noise is generally considered to be the random variable with zero mean. For example, if we take a large number of pixels and compute their average, the noise should be cancelled out. Otherwise, the noise will affect the brightness of the image, will not be considered as a noise at all. Because of this zero mean property of the noise, traditional method in the OpenCV package use the non-local mean denoising. The idea is simple. Given an image, we find a similar patches and then average out the noise. Now we go to the machine learning time. We need to learn a good image denoiser. Specifically, the image denoiser is denoted as a deep neural network, taking input the noisy images and giving output a clean image. However, in practice, we only have clean images as the training data. To solve this, we construct the noisy images by adding Gaussian noises with zero mean of various levels. Then we can train a good deep image denoisers that performs much better than the conventional non-local mean denoising method. However, although deep neural network has good performance, it is vulnerable to the adversarial attacks. Similarly, this also applies to the deep image denoiser. To explore this, we ask a research question. What kind of zero mean noise that can make deep image denoiser fail? To answer the above question, we design the zero mean adversarial attack to evaluate the vulnerability of the deep image denoiser. To realize this attack, we use the PGD method, but this PGD method has two constraints, which is different from the conventional one. First, the noise should be bounded by the adversarial budget, which is the same as a conventional PGD. Second, different from the conventional PGD, the noise should meet the zero mean property. To realize this, we customize the projection function pi in the PGD method. To meet the zero mean property, the projection function pi should project the adversarial noise onto the zero mean plane. The zero mean plane consists of the vector z whose mean of its element equaling 0. How could we project the vector delta onto a plane? First, we find an all-one vector that is orthogonal to this zero mean plane. Then we project the vector delta along this direction of this all-one vector. Then the adversarial noise delta minus this new projection leads to a new vector, that is black one, that is on the zero mean plane. Now we have our two-step projection pi. The first step is to meet the zero mean constraint. The second step is to meet the adversarial budget constraint. For example, a deep image denoiser can effectively handle the normally noisy images and remove the noise to reconstruct the clear images. By comparison, if this noise is corrupted by our zero mean attacks, the performance of deep image denoiser is severely destroyed. We can clearly see some blurs remaining on the roof and some strange contours appearing in the sky. Therefore, our zero mean attack can indeed uncover the vulnerability of the deep image denoiser. Then, how could we make deep image denoiser robust? The solution is adversarial training. During the training, we add an additional loss term to encourage the output of the adversarially noisy images to be similar to the output of normally noisy images. Therefore, we train the deep image denoiser using both adversarially noisy images and naturally noisy image to ensure that the reconstruction quality is high and the reconstruction is robust. To realize this learning objective, we alternatively use the PGD method to generate the adversarial noise and then minimize the above two loss terms with respect to the model parameters. Then compare with the standard training, our adversarial training can ensure the reconstruction qualities under the adversarial attacks. Last but not least, we surprisingly find the robustness of the deep image denoiser can also benefit the generalization capacity on those unseen real-world noise. In other words, robust deep image denoiser can denoise the real-world noise even without training on those real-world noisy images. We guess it is because adversarial attack can explore the worst case noise. Learning from those worst case noise can make deep image denoiser dealing with various types of unseen noise. Let's look at another example. Two-sample test. Two-sample test is a statistical hypothesis testing, judging whether the two sets of samples are drawn from the same distribution. It is widely used to analyze the differences between two batches of data, which is applied in many domains such as physics, chemistry, biology, so on and so forth. It is used to check whether their scientific experiments have made significant changes or not. Then how to test? We first define a test statistic. The test statistic measures how different the two batches of data are. Then we compute the p-value of the test statistic. P-value is the probability of observing this value of test statistic given the known hypothesis that the two distributions are the same. If this p-value is very low, we reject the known hypothesis. Let's look at a simple example. Suppose we have two batches of apples of various size from two companies. We want to know whether these two batches of apples have the same quality. Let's first calculate the t-test statistic. XP bar is the average of these 5 apples. XQ bar is the average of these 5 apples. Sigma p is the standard deviation of these 5 apples. Sigma q is standard deviation of these 5 apples. NP equal to 5, NQ equal to 5. Suppose we finally calculated and get the value of minus 2.44. We really want to know whether this value is large enough to tell any differences. Therefore, we look at the distribution density functions of the t-test statistic. We found the probability of this test statistic under the known hypothesis is very low, below 0.05. Then we reject the known hypothesis and conclude the two batches of apples are different. In practice, t-test is very limited. It cannot handle the complex distribution. Therefore, we need to use the general purpose test statistic. However, computing quantile of complicated test statistic under the known hypothesis is very tricky. To solve this, we use the permutation test. First, we randomly shuffle the joint set of SP and SQ into the S1 set and S2 set. We can treat S1 and S2 coming from the same distribution. Then we compute the test statistic of S1 and S2. Then we repeat. For example, we can repeat this process 1,000 times, even 10,000 times. Then we can plot the empirical CDF of the test statistic under the known hypothesis. Finally, we can locate our test statistic here. Then 1 minus this value is the calculated p-value of the test statistic of SP and SQ. Now, I will introduce a general purpose test statistic, maximum mean discrepancy, MMD. MMD measures the differences between the distribution P and Q, which is the largest differences in expectation of all functions. However, in practice, we only have limited data. We must restrict the function class to provide the useful finite sample estimates. But we also want this function class, curly f, to be rich enough to become flexible. Therefore, we choose curly f to be the unit ball in a reproducing kernel Hilbert space. Then we can define the kernel mean embedding to embed the distributions into infinite dimensional feature space. This can allow us to compare and manipulate distributions using dot products. Then due to the reproducing property, we can make the soup disappear and use kernels to calculate and compare distributions. Finally, if the MMD equals 0, the two distributions are the same. Then then actually we can use different estimation to estimate the MMD. This is a large area of research here. Let's make our notation simple here. We denote MMD hat square estimation by kernel K parameterized by theta. Then how to test with MMD? First, we fix a kernel and its parameters, such as we use a Gaussian kernel and fix its length scale. Then, given two sets of data, SP and SQ, we calculate the MMD estimation. Then we use the permutation test to estimate the p-value of the MMD estimation. Then lastly, we reject the null hypothesis if this p-value is too small. Now we go to the machine learning time. We should learn the kernel parameters from the data. We can use the deep kernels, and the theta is parameterized by a deep neural network. Then how to learn the parameter theta? We first split the data SP and SQ into the training data and test data. Second, we define a learning objective and optimize and learn the kernel parameter theta from the training data. Then we conduct the normal two-sample test on those test data using these optimized kernels. The next question is how to define the learning objective. The learning objective is a test power. The test power is the probability of correctly rejecting the null hypothesis when the alternative hypothesis H1 is true. Then, due to the symptotic of MD and the alternative hypothesis, we can use the central limit theorem. R here is the rejection threshold decided by the permutation test. Big theta is the CDF of a standard normal distribution. Then for the large N, the first term dominates. Then we can estimate the kernel parameters by maximizing this term. Once we get the optimized theta kernel, then the two-sample test become very powerful, can tell in very tiny differences of two distributions. Now, I consider a potential risk that can cause a malfunction of non-parametric two-sample test. To this end, we use the PGD method to minimize the test power on the test data to search for the adversarial pairs. For example, we have lovely images of cat and dogs. The non-parametric two-sample test can correctly differentiate the benign pairs of cat and dog coming from the different distributions. But it will wrongly judge the adversarial pairs. They all think they are coming from the same distributions, which are clearly wrong. Then, to robustify the non-parametric two-sample test, we propose use adversarial training to train the robust deep kernel. In particular, it is formulated as a max-min optimization that is similar to the adversarial training's min-max formulation. For its realization, we interactively generate the adversarial pairs by minimizing the test power, and then update the kernel parameters by maximizing the test power on those adversarial pairs. Then finally, we can obtain the robust kernel. Then the two-sample test with this robust kernel can have a very good testing capacity and resisting against the adversarial attacks as well. Then this is the last slide. The take-home message is traditional method has limited performance. Now we go to the machine learning time. We have a machine learning method which have good performance but are vulnerable. Now we really need those robust machine learning methods that have good performance and are robust as well. Thank you.
So today I'm going to talk about the Lie group Bayesian learning rule, which was accepted at AI Stats. So this is joint work with Thomas Möllenhoff and MTS Khan. They're both from the RIKEN AIP Bayesian inference, approximate Bayesian inference team. I myself am from the mathematical science team of AIP, which is basically a bunch of mathematicians and physicists. So the Bayesian learning, what is it? So it learns, instead of learning a single optimal value of a parameter of a machine learning model, it learns a distribution over the parameters. And there are some notions of a prior knowledge and updating your distribution as new information can come in. So the Bayesian setting has some practical benefits such as uncertainty quantification, robustness, reduced overconfidence, and as I said, because of this updating notion, it's a promising direction to look for continual learning. But as a mathematician, I kind of like the fact that also I like more the fact that there's a lot of rich mathematical structures here, and it is structured enough. So there's a lot of interlocking mathematical objects, which are also flexible, but not too flexible. Like, I don't know how to say this, but I think it's a good middle ground for flexibility. And then we can use these objects as a guiding principle for designing new algorithms. I mean, for example, like designing a variant of, I think, SGD, at least in my case, it's like too flexible. Like there's a lot of things you could do. It's guided more by intuition. So the Bayesian learning rule, which our work is an extension of, was developed by MTS Khan and Howard Drew, and it yields by approximations and some specializations a wide range of Bayesian and non-Bayesian algorithms. But it also has been able to help design new algorithms, and our team, the ABI team, has been able to already use it in designing new and successful methods for learning. So such as variational online Gauss-Newton, variational Adam Bayesian SEM, that's sharpness aware maximization. But like classically, though, the methods that have worked well are also like special cases and approximations after that of this Bayesian method, this BLR. So let me maybe dive into the mathematical thing right now. Let's start with a loss function. So this is this is a familiar setting. We have a parameterized machine learning model with parameters theta and we have some data, and the loss function, the way this model and the data are baked into the loss function itself. For example, they could be your neural networks, with theta being your weights, or something more classical like ridge regression, and theta are your regression coefficients. So in the classical setting, what one would do is try to find a risk minimizer, a single theta star, which minimizes this loss. In the Bayesian setting, this is our problem. So what we're trying to find is a distribution over the parameters. And this objective function, which is a functional of this distribution, consists of two parts. Like that are maybe in antagonistic relationship with one another. So there's the expectation term. So you can even see this as like an implementation of the exploration-exploitation trade-off. So you expected loss, we want it to be minimized. And if it were only up to this guy, then what it would do is try to concentrate almost all of the mass of the distribution near a global minimum, almost become like a Dirac delta function. So we wouldn't really get a new problem. We would get the classical problem back if it were the old, if it were only this thing. But this is balanced off by the entropy term, which prefers higher distributions which are more spread out. And so it wants to explore more around the parameter space. And this loss could be a very complicated function. For example, in the case of this neural network. So you might see like this if we're taking this space of all distributions, the expectation term is linear and like the minus entropy is strictly positive. So actually, at the cost of going to infinite dimensions, in a sense, which is a big cost, but we have kind of simplified the problem. And actually, if we're thinking about all distributions, there is a solution. There's a unique solution. It's called the Gibbs distribution or the Boltzmann distribution. And that is a distribution proportional to e to the minus loss of theta, which is not very helpful because I mean, if loss was a complicated function, then e to the minus loss is equivalently complicated. So we approximate with a family of distributions, candidate posteriors, if you will. And we search for Q in there. So Q could be like your Gaussians or some other family which you like, which is a finite dimensional manifold of distributions. Now the uniqueness of the solution is gone, but I mean, we have a more approachable solution problem now. And this is the approximate in the approximate Bayesian inference team name. So what the BLR did that I mentioned before is consider exponential families. So BLR, the Bayesian learning rule, works for exponential families. And so these are distributions, members of this family are distributions of the form e to the minus lambda transpose time t, where t is a sufficient statistic. It's a function, possibly continuous function, from theta to theta to a vector space, and lambda in the dual space are the natural parameters. And the BLR is an update rule. So all the distributions are parameterized by lambda. So the update rule given in BLR is an update rule in lambda. And this is natural gradient descent on the lambda parameters. So we have the gradients in lambda of our objective function that was on the previous page. And multiplying with this Fisher matrix means that we are taking the gradient descent with respect to the Fisher information metric, the Riemannian metric that is on Q, which is like a very nice family, has many favorable properties on the statistical manifold Q. So each point of which is a distribution. So, I mean, I've already extolled the virtues and like the depth of applicability of the BLR on the two previous slides. But there are certain issues with BLR. Okay, the first one is not really too much of an issue, but this setting, the Q needs to be an exponential family. There are a lot of nice exponential families. You have the Bernoulli distribution, Gaussian, Rayleigh, gamma, inverse gamma, Wishart. So many families you know and love are in here. So maybe this is not too bad, but you might feel a little claustrophobic by saying, oh, do I have to be an exponential family? Can I not choose something different? Secondly, slightly more important, is that so not every lambda is actually allowed. So think of the Gaussians, then we have T of theta is a two-dimensional vector here, theta, theta squared, and we have lambda 1, lambda 2. For this to be normalizable, to be integrable, you need lambda 2 to be positive. But the update rule is acting as if we're in the full vector space of lambdas. This is a linear update, so it could very well be that we could overshoot the constraints and get non-admissible, not allowed lambda. And we could overshoot. So what you would have to do is project back into the space. And so I mean, that's possible to do, and it has been done, but you have to do it. And it's not only this rule then. And thirdly, computing the gradient of this objective function, which involves an expectation, is not always possible. It's not possible to do in every case. In the full generality of exponential families, there is, I mean, it's always done with certain tricks with respect to special exponential families. And there is no like seamless way to do it once and for all of them, once and for all. So our proposal is to take a Q, which is not an exponential family, but we add another structure, a different structure to it, which is that Q should be parameterized by a Lie group. So we have a group G that is acting on the parameter set theta. And therefore, it also acts on distributions on theta. I'll give examples of this by push forwards. And then by taking a base distribution Q0 and pushing it around with the group of the Lie group action, we get our family. We say this is the orbit of Q0 is our family. And now every group element is a distribution in our family. So it gives a distribution in our family. So the distributions are parameterized by Lie groups. So what are some examples? Let's take the Lie group to be the real line with the additive operation acting on itself. So then it acts on distributions on the real line by translation. So the Q0 would go to Q0 theta minus G. If Q0 was centered at 0, now it's centered at G. Or if we have the group of which is positive reals acting multiplicatively on itself, then a distribution like Q0 here would get scaled and also suppressed because it still needs to integrate to 1. And or you could have a combination of the both with the affine group. And notice that if Q0 is like the standard unit normal distribution, then with the affine group, we get the set of all normal distributions. So the normal family actually also fits into this group setup. So maybe not everyone is familiar with Lie groups. So let me have a quick, it can't be a recap, but like a few elements of what is a group. It's a set with a binary operation. This is like very abstract, immensely general. What's important is that we can multiply elements of G with this binary operation, and it satisfies certain axioms, such as like there's an identity element and E times G times G times E, or they're both G, and like there are a bunch of other axioms like associativity. It's also a manifold. So a Lie group is on top of being a group is a manifold. It's a smooth manifold, and so you can differentiate, and therefore you can consider directions. You can differentiate a path, and it will give us tangent vectors on the manifold. And there is a special map in a Lie group called the exponential map. It's a global retraction. We don't need to assume a metric, a Riemannian metric on G, but this exists regardless, this exponential map. It goes from the tangent space at identity, also called the Lie algebra, and then wraps this flat vector space onto G. What that allows us to do is that we can consider paths in G. Let's say this path, exponential of tx, where x is a vector in the tangent space, the Lie algebra, and then that path, when we differentiate it at identity, we get the vector x. So we have this notion of going on the group, staying on the group, but going in the direction of x. And if you want to do this at G, you just multiply the whole path by G at a element in like small g in here, and then the whole path gets carried over there. And then at G, you would be going in the direction of x again. Notice that, or the push of x. But now all the directions are actually parameterized by a single vector space, the vector space at identity. This is what's great about the Lie group, that it's also a very homogeneous object. We can carry every point to every other point by these multiplication maps. If you want some examples, matrix groups are great. So for example, invertible matrices or orthogonal matrices, or like the SLN, all considered with matrix multiplication would be a group. There are certain examples of groups which cannot be represented as matrices, but many of the Lie groups that you're gonna encounter in the wild can be considered as matrix groups. So I doubt that you would encounter anything else in machine learning. All right, so what's classical learning? Classical learning, like gradient descent, we would be at a theta, a point, single point, and then update our theta along the direction of the gradient of the loss function. So these are the contours of the loss function until we reach a point of low loss. Updating a distribution means we are updating the whole distribution until the whole distribution itself settles in a region of low loss. But now, since our distributions are parameterized by group elements, we can use elements of group theory of Lie groups that in order to design an update rule, and we can use the exponential map that I said. So this is a group element now, and G times the exponential of alpha y, that's a group element times another group element. The left-hand side is always a group element. So then Q sub G, or with G on the left-hand side, will always be an element of our family. It's always in the family. And y here is the direction of fastest ascent, because minus y is descent of our objective function, this curly e. So, and it is, okay, so when I said fastest ascent, I need to specify with respect to which metric, otherwise it doesn't make sense, but with respect to the Fisher metric, because we want to keep in touch with the BLR method. And there are some benefits to it. So y is an element of the tangent vector at identity. So we then can solve certain issues with BLR. Q is not required to be an exponential family anymore. You can choose your base distribution freely and push it around with a group. The updates will always stay on the manifold by design, so that like we will always have a Q. I mean, the answer is the update will always give us a G, and Q sub G is always going to be a distribution in our candidates family. Well, and the gradient can be the reparameterization trick to compute the gradient can always be done. So let me spend some time on this. So calculating the gradient, this involves calculation of the gradient of an expectation with respect to the parameter of the distribution. So because of the way we created these Q sub G's as push forwards, by changing, so this is by this equality is definition, and then by changing of the variables from theta to G times theta, the G gets pushed away inside of L. So this is exactly true, and you can find the details of this in our paper. But it's not, it's actually like, very easy. It's like 1 or 2 lines, 1 line. And now all the G dependence is inside of L. And once we take the derivative by chain rule, now we have, this is the standard point-based gradient, which we can, of the loss function, which we can, if this was a neural network, we can calculate this by backpropagation. And then we can sample from Q0 and then evaluate this as an expectation of by MC sampling. So this is also called pathwise gradient estimators. And what's the important point is that the group action, this Q, is the correct framework in which we will have pathwise gradients estimators. These paths to estimate these gradients. And it works seamlessly in, like, very easily in all of these cases. So it's not just for a couple of special families like it was in the exponential family case. There are a few bonus features. The Fisher metric, which is being calculated at Q sub G and being carried to the identity tangent space. Well, it doesn't matter from which point we carry it back to the identity. This bilinear form is being carried to the tangent space. It is invariant. So the Fisher metric needs to be calculated once and for all, because and that's it. And the tangent directions, they are all the y's, because we've written our update rule in such a way that all of our y's, the tangent directions, are lying in the same vector space. So it makes sense to accumulate previous steps, and we can implement things like momentum. So this is trivial in like standard gradient descent, but on gradient descent on a manifold, like each of your vector spaces would lie on a different, each of your updates vectors, gradients would lie in a different tangent vector space, and they couldn't be meaningfully added. But because of the homogeneity of the group, we can do that. And we have implemented it, the momentum. So, okay, this was all very abstract. So what does it mean in practice? So for the additive group, for some special groups, this is the update rule. It's the expectation of the gradient is being subtracted from the group element. So this is almost like your standard gradient descent. If Q0 was like very close to the Dirac delta distribution, then the Dirac delta, then Q sub G would be like the Dirac delta distribution centered at G. And then the gradient of L would be sampling just the gradient of L at this expectation would be sampling the gradient of L at G. If, however, Q0 is a little more wide to begin with, then what we do is that instead of evaluating it exactly at this point, the gradient, what we do is we sample from around the point of the gradients, and then average them out and decide where to go by the consensus direction. So we're injecting a little bit of noise inside the gradient. So this actually had been thought before, this injection of noise inside the gradient by more heuristic means. But then the multiplicative group update rule and the affine group update rule are not. Like they are new. One thing to note might be that all of the gradients are inside of the distribution here. So they all learn, but they learn differently. So maybe let me talk about like one example of how they would learn differently. So we have, let's say, the multiplicative learning rule. We can set certain nodes of the network to be inhibitory or excitatory. So fixing the weights, signs of the weights, the magnitude of the weights are either excitatory or are the parameters. And let's look at the first hidden layer and look at all the edges that come from it. And these weights act as a filter, detecting certain things from the image. And we can look at the weights, and they ended up being sparse and localized. So comparing additive, which is like SGD, they both learn. We can see that they learn but they learn differently. So here's what I mean. These are the most activated filters of with respect to this MNIST image. And the information is there because they did learn, but you can see that the filters are different on both sides. And these are very sparse. And like for MNIST, I could even like do this trick. I could say, what is like the green or red vertical stripe in the center? And you would be able to say it's, hopefully, you would be able to say it's this one. Whereas on the left-hand side, I think it's much harder to describe it in like few human words, which filter I'm talking about. So I think this is a nice area to explore. All right, wrapping it up. So current work. So BLR is also able to bring the derivative inside the expectation, but only in certain exponential families like Gaussian. So this reparameterization trick is possible. But those are actually the ones that also fit the group framework. So we're doing a work with Koichi Tojo and Kenichi Banai from the mathematical science team. They have a recent work which characterizes all the families which are exponential families and have this group action. And in those cases, the push forward of a distribution gives you an update in lambda. And what happens is that now we have an update rule in lambda, and if we linearize this, then we get the original BLR. And this is actually a wide family of, this covers a lot of distributions. So these are all the cases where we can take the reparameterization from outside the expectation to inside. Well, of course, you can't do it in here. There's nothing to differentiate in the sample space, but in the cases where you can always differentiate in the sample space first. Okay, so the Bayesian learning rule is a promising and fertile setting. The BLR of Khan and Ru, both specialized to many, gave a lot of new existing and successful algorithms. But there are certain issues such as closure of the updates with respect to, well, in the staying on the manifold and calculation of derivatives, doing it seamlessly. So the group framework solves the closure problem by design, and it's able to generally employ the reparameterization trick. And each new group, okay, so here are some maybe limitations that each new group, we don't know if they would necessarily learn your standard data sets. We would have to test that out. And even if they learn, they might have different learning behaviors like we saw in multiplicative and additive. So that's some work to do there. And also there might be implementation problems with arbitrary groups, such as like the exponential map of a million by million matrix might not be easy to calculate. Oh, okay, I'm done here.
My name is Qibin. I'm working in RIKEN AIP. Today I'm going to talk about efficient machine learning with tensor networks. As we know that now the foundation model and the generative model achieved remarkable success. And it always has three important factors. It always needs very big data set, and it need a lot of high quality training data. And the model becomes larger and larger. The number of parameters will reach 175 billions or even more for the like GPT-4. And of course, it also need a lot of training computation resources and cost a lot of money. So from the model perspectives, as we know that over-parameterization is a successful technique, and it demonstrates to be successful to avoid overfitting and achieve very high performance. But our question is, if we really need such a large number of parameters to achieve the same performance, actually such complex architecture, it gives us a lot of computational costly for the training and inference. And at the same time, due to the very complex architecture, it's very difficult to interpret how a neural network works internally. and it lacks of robustness to the adversary attack. So we are wondering how to dramatically increase the model capacity, but without significant increase the model size. In other words, that if we have the same performance, can we dramatically reduce the number of parameters, or can we have the same number of parameters but dramatically increase the model capacity? Okay, before I introduce how to solve this problem, maybe I briefly introduce the tensor networks. When the data is a matrix, as we know, the matrix factorization is a very important tool from mathematics for dimension reduction or feature extraction. When the data becomes three-order tensors, there are also some popular tensor decomposition or tensor factorization to capture the structure of data, like low-rank SVD or high-order SVD or CPD Tucker decomposition. But when the order becomes much larger than 3, it becomes a very complicated model, and it has many flexibility and the capacity to capture more complex data structures. So we call this tensor networks. And in tensor network, actually, in physics, they use tensor network as a very powerful tools to study it quite earlier. There are already some tensor network model like train structure or two-dimensional structure or tree structures. So conceptually, in general, tensor network is a kind of tools to represent the n-order tensor as small tensors. And all the small tensors are contracted or connected. Such connection is some kind of contraction operation to represent the huge data or huge function, something else. So this is the one particular example. We call this tensor ring decomposition. So as we see that given a high order tensor X, we can represent X as n small core tensors, and each core tensor with much smaller size than X. And all the core tensors are connected as a ring structure. The connection is some kind of contraction, as I said before, on specific mode. So how to understand this tensor ring representation? Actually, given an element with n indexes, we can see that each element is equal to a product of a sequential matrix. And each matrix is extracted from the core tensors according to the index on each mode. Finally, the trace operation makes it becomes output is a scalar. So this is a tensor rings decomposition. Actually, there are many different types of tensor networks. So each tensor network may have different property or structures. It depends on the data and your task. So now I will introduce how to do the parameter efficient modeling by using tensor networks. So one task is to do the model compression. That means we already given a pre-trained neural network. We try to reduce the number of parameters, but keep the same performance. So actually, of course, after you train a well-trained neural network, you can, after training, you can take out the weight parameters. Then you try to reduce the redundancy information by using the tensor network or tensor decomposition. So after training. Another way is you can start training at the beginning. You give assumption that the weight parameters satisfy some structures like tensor network. Then you apply the standard training algorithm to learn the core tensors. So we hope our compression technique satisfies that, doesn't affect our algorithm. So that means standard algorithm can be applied to the model compression technique. And in the end, we also expect to achieve the computational efficiency by not only the memory saving, but also computational time saving. And this is one typical example that using tensor network to do the model compression. And here is a fully connected layer. We assume the weight parameters W is large matrix. And how to do this? So actually, it's quite simple. We first tensorize W as a high-order tensor. Then we represent this high-order tensor as a tensor chain structure. So by using this, we can see that the size of matrix W from the original size is Mn. After representation, actually the size it will be reduced to this root of Mn. But of course, there's another value R, which is a tensor network rank. So that means we hope that parameters W has a good structure, like low rank structure. If the rank is very high, like if the W is totally random, we don't have any data structure, then we cannot achieve good compression rate. So another point is from computational efficiency. Since the W is represented as a tensor network, then all the latent layers and the output layer can be also tensorized as a high order tensor, and even decomposed by the tensor network. Then all the operation can be performed according to the rule of tensor network operations, which is quite efficient because each core can be contracted with original 10 core tensors in parallel. So to understand why such tensor network can do the model compression, we use a simple linear latent factor analysis, which shown here. Then we assume our data Y can be tensorized as a high order tensor. Then if we marginalize the latent factors eta, we will get a Gaussian distribution and with the covariance. Since the Y is a tensor, now the covariance matrix is becoming the covariance tensor. So using the standard way, we try to do the decomposition of the covariance tensor using the tensor network, which is an extension of matrix decomposition. So we can estimate the W. So finally, we can see that in order to find the most principal component or the mean information of Y, actually, we can assume the W is represented as a tensor network. Then it also gives us implicit assumption is our data Y is a high order tensor. That means have some kind of structure, high order structure. So, but in our neural network, our input is not always have a very high order structures. So one trick is we can create a tensor from the input layer. So this is an idea from the quantum inspired system. We can mapping our input, which is a vector, and to the tensor network. So how to do this? So take out each feature and we mapping to a two-dimensional vectors, which can correspond to the probability of this bit to be 1 or 0. Then we're using the tensor product of all the features. Such mapping is nonlinear mapping. Then from the input data, we will get a tensor network structure. Such tensor network structure is very low rank. It's a rank 1 tensor. So using such trick plus the model compression by the tensor network, actually they can show that we can achieve comparable performance on the MNIST data set and using only one layer. So next, to go further, next question is, can we keep the same number of parameters but dramatically increase the model capacity? So here we show that we propose a tensor polynomial pooling layers. So this is similarly using a tensor product and a tensor network for the weight parameters. So our input can be like latent features or the multimodal input data or anything else. So first step is concatenate them as a long vector. Then we using the tensor product with itself for p times. So by using such p order tensor product, we can get high order statistic information from the data. Then the next, because our layer is become tensor network structure, so all the parameters can be parameterized by using the tensor network representation. After that, we can get output. So from the number of parameters views, actually our number of parameters view is actually we don't need to compute this tensor out product explicitly. So the number of parameters will be reduced to the linear scale with the p. For the exponentially scale to the linear scales. And from the computational perspectives, so since these two parts are all tensor network, so they can do the operations very efficiently using the tensor network operation. That means each core tensor just need to do the contraction with each f individually or separately. So finally, our model capacity can be increased polynomially, but the number of parameters doesn't increase, only increase linearly. So when we apply this to such technique can be applied to many neural network models. And here is a particular case for the recurrent neural network. So now we change each layer from the standard layer to the tensor network layer. Similarly, we concatenate the input and the latent state X and H together. Then we using the tensor product for p times. After that, we do the linear transformation using the core tensor G. Of course, later G will be again also represented as a tensor network. So here we can see that actually the nonlinear function are removed, because we already using the nonlinear mapping from the input layer. So finally, this is our final formula for this layer. So as we show that when the p is larger, we can achieve the long memory, and the small p will lead to the short memory. And after that, the next is how to represent the G. So in the simple case, we assume the G is very simple case. It's a symmetric tensor, and it can be decomposed as like CPT, a CPT composition, or even the rank 1. Then such layer can be further degraded as this formula. So from here, we can see this is compared to the standard layer. Actually, our nonlinear activation function is changed from the ReLU or something else to the just power p. And here is a summation R. That means it contains a subset of neural network, and each neural network using the nonlinear activation is like this. So next, we can also using the learning strategy to learn the P automatically. So to find the optimal P, that means using this, we can learn the nonlinear activation function simultaneously. So as we show that in the past, many studies using different tensor network, like fully connected layer network, tensor chain, and regression network using the Tucker model or the tensor ring model for convolutional neural network. So the question is how to choose the tensor network structure when for our machine learning task at hand. Usually people using consider this hyperparameters and to tune it by training many times. But we hope to learn this structure automatically. In the past study, it's similarly to the model selection problem. When we do the tensor decomposition, we need to select the rank or select the number of parameters. It's mostly here. So, but now we consider to learn the structure. That means we try to learn which tensor decomposition we should use or which structure we use. And another, in addition, another degree is permutation, which never studied in the past matrix decomposition or tensor decomposition, which we call the permutation. Such property only exists in the tensor networks. So our expectation is maybe the standard tensor network is not optimal for our task. Probably the very random or arbitrary tensor network is the best for the given task. But to learn such structure is very difficult. Like even given the 9-order tensors, there are 68 billion candidates. And it's not a continuous optimization problem. So we formulate the tensor network. First, we encode the tensor network as a graph representation. So we use the node V contains a set of core tensors. And the tensor network structure is encoded as an adjacency matrix. So the number means that these two cores has connection, and the number is the connection rank. So next, we try to learn this adjacency matrix as the tensor network structure. So since our goal is to make like compression or to represent the data more efficiently, so our minimization goal is to minimize the number of parameters, and given the approximation error is smaller. So to learn this is we cannot compute the gradient, or it's not a continuous optimization. So firstly, we develop an evolution algorithm to learn this, but still very slow. And regarding the permutation, I would like to explain the permutation problem. Even the tensor network's architecture is same, like all tensor network is tensor ring, but the core tensors, the order of core tensors are very important. Like 3 order, like 1, 2, 3, have a different order, and we have shown that they have totally different result, and then the approximation error is different significantly. So next, our goal is to develop a very general learning algorithm to learn the tensor network architecture, like topology and the permutation, and also the rank simultaneously. And we have some progress developed algorithm, but I will not introduce detail today. Maybe if you are interested, we can send you the paper. And next, in order to understand the convolutional neural network and the relations between tensor network and the convolutional neural network, we also show that actually the convolutional neural network can be written as another way, like Volterra convolution neural network. And this neural network is consists only one layer. But in this layer, there are many small sub-neural networks. Each sub-neural network is high-order convolution. So it's not just a convolution, it's a high-order convolution. As we say that, for example, this is the first-order convolution, is the second-order, this is n-order convolution. And they make summation of all neural network, gives the output. It's theoretically is almost equivalent to the original neural network. But here is a high order convolution that kernel, our tensor kernel is a tensor. And this part is a high order convolution. Actually, it's very similar to our previous presented is a tensor pooling layers. And we can see that using this net, we can approximate original CNN very precisely. And also we can learn the perturbation using the VC network easily. Such perturbation can also attack the original CNN. Due to the VC network, we can also giving the upper bound of sensitivity of functions. So which is easily to study the how robustness of our model to the perturbations, which is very sensitive to the order n. So finally, maybe for the computational efficiency, I will introduce how using the tensor network to solve a very basic mathematical operation, which is matrix multiplication. So given the matrix multiplication, the standard algorithm usually need like a 2x2 matrix, need 8 multiplication. But the fast algorithm using Stochastic algorithm, actually we can reduce the number of multiplication to 7. But when the matrix becomes huge, it's very difficult to find the fast algorithm. So one method which proposed by DeepMind researchers and published in Nature last year is to using the tensor net decomposition to find the fast algorithm. So first we can encode the original standard algorithm into the tensor. Then using tensor decomposition, we find the latent factors. Latent factors is corresponding to the fast algorithm. And the rank is the number of steps we need to compute. So if the rank is smaller than original element, it means we can compute matrix multiplication efficiently. So here's some results that for the larger matrix, actually we can reduce the number of multiplications dramatically. But it also shows that this result is not optimal, because some mathematicians show that for the 5x5 matrix, 96 is not the minimal number of multiplication. We can even find the better algorithm. So that means such algorithm is not perfect. We still like tensor decomposition is maybe not algorithm has problem to find the minimal rank or something problem else. Another direction is quantum neural machine learning or quantum neural network. So this the input is quantum state. It's very similar to my presented how to do the nonlinear mapping for the standard data. And here is the quantum circuit. Actually, the quantum circuit is unitary transformation, which is very simple and has strong relationship with tensor network. But the current quantum neural network has problem like the error corrections and the limited capacity for models, and also the limited input qubit. So the performance cannot compete with the neural network, but it's potential directions. If someone has from the physics, I would like to collaborate with them. So this is summary, and finally, I would like to thank my team members and collaborators.